So we're continuing our talk about transformations today with the two that we haven't talked about yet, and those are rotations and dilations. So we'll start with rotations. Okay, so remember the vocabulary word from yesterday. If something is a congruent transformation, that is called an isometry, which means the image is congruent to the pre-image. Okay, so after the rotation, that triangle, that quadrilateral, whatever, is the exact same angles and the exact same side lengths as the pre-image, the one that you started with. Okay, a rotation, let's see, how about we do turns? It turns an image. Okay, we could also say rotates, but a rotation rotates. I mean, that's kind of redundant. Around a central point. Okay, a central point of rotation. Orientation is definitely change. We are not preserving the orientation when we do a rotation. So it will change from up to left to down to right, whatever we have to look at. So here are your generalities, right? Your notation. If you have a 90-degree clockwise or 270-degree counterclockwise, right? So a clock, we have 12 at the top, and then 3 o'clock, and then 6 o'clock, and 9 o'clock. So traditionally, a clockwise is a right-wise rotation. Okay, and then counterclockwise goes the other way. So if we're going to do a 90, right, 90-degree rotation is from 12 o'clock to 3 o'clock. Or if you're going to do counterclockwise, that means we're going the opposite way of a normal analog clock, and we end up at the same position. Okay, so the x and the y's change, right? The x and the y's change position like they did yesterday with a reflection, but the new y value is negative and the new x value stays the same. Okay, so it's going to take a little bit of getting used to, but this is your general notation for a rotation. So let's practice some of these. A 90-degree clockwise around the origin. Okay, so there's two ways that we can think about this. So this point right here is going to be held steady. Okay, so if this was 12 and this is 3 o'clock and this is 6 o'clock and this is 9, we're going to rotate our thing 90 degrees clockwise, which means we're going 3 o'clock is going to become where 6 o'clock is, and 6 is going to become 9. So this is how our shape is going to look when we're done. Okay, so if you have a piece of paper, you can twist your piece of paper to give yourself kind of an idea of where this is going to end up. Okay, sometimes they have paper called patty paper, which is see-through-ish, right? Some kind of a paper that you can twist and see. But we're going to use our notation in order to do this for us. Okay, so the notation is for a 90-degree clockwise rotation, the x's and the y points switch, and then your x becomes negative. Okay, so let's see if we can do that. Here we have point A. A is at 4, 3. Here we have point B, which is at 3, minus 1. And point C is at 8, minus 3. So those are your three original points. Now let's use our rotational notation. So we're going to switch your x and your y coordinate, and you're going to make your original x negative. Right? Your original x value is going to become negative. So that means A prime is going to end up at 3, negative 4. B prime is going to end up at negative 1, negative 3 because your x changes. And C prime is going to end up at negative 3, negative 8. Okay, the y value stays the same. It just becomes your new x, and the x value changes sign. So let's plot 3, negative 4, 1, 2, 3, and 4 down is right here. There's A prime. B is negative 1, negative 3. B prime is here. And C prime, negative 3, negative 8 is down here. And of course, we're going to shade your image. And there is your 90-degree clockwise rotation. So let's check out our next one. Example 2 says a 180 rotation around the origin. So if we look at our notation for that, we switch your x's and your y's. Nope. We just make them both negative of what they originally are. So whatever your x and your y values are, we make them negatives, and that does a 180 rotation. So now we have 4 points. A is at -6, 2. B is at -1, 0. C is at the point 0, -6, it looks like, and D is at the point -5, -3. So now we're going to do our 180 rotation and make all of your values negative. So the negative of -6 is +6 and a -2 for A prime, right? A prime, my notation. B prime, we're going to make -1 into a negative, which is a +1. 0 doesn't change. 0 stays 0, of course. 0, and now we have a +6 because C was a -6, and then D is going to be at D prime, +5, +3. Okay, so let's plot those points and shade. So there we have your 180 rotation. So we're going to do these other ones. Let's see, what else do we have here? We have a 90 counterclockwise. Let's see where our 90 counterclockwise goes, which is the same thing as a 270 clockwise. So here's our, now we switch them and the x, or rather the y, becomes negative. So that's what we're going to use as our notation, -y, comma, +x. The negative of the y value and the same as the x value for a 90-degree counterclockwise. So now we're coming this direction around your origin, right? We're still doing an origin rotation. So there's your 90 counterclockwise around the origin. And then our last one, the 270 clockwise, which is the same as your 90 counterclockwise. Let's see, 270 clockwise, where's that one? 90 counterclockwise and 270 clockwise are the same. So negative y, no, is that what it was? -y, comma, x. Okay, so there's our rotations around the origin, right? We have rotations around the origin, which have these special rules to them that we can apply to change our points and move them around as we do our rotations. Okay, so now let's get a little bit more challenging and do some rotations not around the origin. Okay, so this is going to require us to do a little bit more thinking and processing. If the rotation is not around the origin, the procedure is different. There's no notation for this. So we're going to do a 90-degree counterclockwise. So remember, that means we're turning this direction. So from the first quadrant, we're going to end up in the second quadrant. Around the point 2, 2. So this is like our origin. So we're going to draw in some new fake axes. Okay, so this is your new fake axis. Okay, so if we're going to rotate around a point, let's draw in some axes. So to make it as close to what we were doing a second ago as possible. Okay? So when we do these rotations, here we're rotating to the left. If your point is up, here, it's going to end up to the left. Right? And if your point is to the left, it's going to end up down. So we're going to move one box away. Everything is going to move one box away to its left. Okay, so let's just think about this. If our A point is 1, 2, 3, 4, 5, 6, 7 up and 1 to the right, 7 up and 1 right from our origin, okay, it's going to become 7 to the left and 1 up. Right? Each of our boxes moves over to the next one. So if we go up 7 and right 1 and do a 90-degree rotation, that means we're going left 7 and up 1. 1, 2, 3, 4, 5, 6, 7, 1. Great, right over my line there. So this is where your new A prime is from your origin. Remember, we're counting from here. That is our point that we're counting from right now. Okay, point B is 1, 2, 3 units up. 3 units up and 0 units over, so 3 units up and 1 unit over, so 0 units right. So our new point is going to end up 3 units left and 0 units up. 1, 2, 3. Here is where your new B value is going to be, right there. Okay, so we're changing your boxes a little bit. It's not very easy to think like this. So point C is 1, 2, 3, 4, 5. 5 to the right and 1 unit up. 5 units right and 1 unit up. So when we do our 90-degree rotation, the right goes in what direction? The right changes to up, and the up changes to left. Right, we're doing 1, so you up, left, down, and right. Right, we're going 1 unit to the left. So up becomes left, left becomes down, and so on. So we're going to go 5 units up, 1, 2, 3, 4, 5, and 1 unit left to end up with our C prime here. Okay? Right, it's probably the first time you've ever done this, so we're going to do another one. We are, right, it's really an exercise in mental thinking. This is not easy to do, and nothing that you would ever think to do as you're driving to work on a Tuesday morning, right? It's not something that we do often. We really only do it in a geometry class, unless this is your job to do three-dimensional rotations and stuff. Then you don't really think like this very often. So let's see if we can do another thinking on this one. A 180 rotation around the point -3, -2. Here we go. So there's our other negative. The -2 should be here. So our center point is -3, -2, and we're doing a 180 rotation. Okay, so this one hopefully will be easier for us to think about, because 180 means we're doing the opposite, right? Up becomes down, left becomes right, right becomes left, and so on and so forth. So we have left, up, right, and down. And our point is -3, -2. Oh, okay, -3, -2. Why did I put it here? Let's see if we really know what we're doing. -3, -2. Okay, so once again, we're going to count from our new origin. We're counting how far left and how far up and how far right and how far down are we from your new origin point. Okay, point A is 1, 2, 3 units left and 1, 2, 3, 4, 5 units up. Okay, so point A is 3 to the left and 5 units up from your origin, right, from your new origin. So if we do a 180, right, left becomes right, up becomes down, we're going to go 3 units to the right and 5 units down, and that's where we're going to find A prime. So we go back to your origin, we count 1, 2, 3 units left, 1, 2, 3, 4, 5 units down. Okay, so we're switching our thinking. Left becomes right, up becomes down, and vice versa. So point B is 1, 2, 2 units to the right, 1, 2, 3 units up. So point B is 2 right and 3 up. So now we're going to switch and go 2 units left and 3 units down. Okay, this is where we're going to find B prime. 2 left and 3 down. B prime is now there. Okay, we're going to do a similar thing with C and D. messed up on D. D's only 2 over. D is 2 over. Okay, so you're not going to have to do this very often, but just in case you are, then you need to be able to count, right? So you have to reverse your brain and think of it in a different way. And there you have your last one. Okay, so now that we've got our rotations, let's get to talking about your dilations. Okay? Dilations are more special. Okay, so if you've ever had or gone to an optometrist, somebody that focuses on eye health, right? You might have had your eyes, what they call, dilated. Okay, and what happens when your eyeballs get dilated is your pupil enlarges, right, artificially, so that the optometrist can shine a light in to see the back of your eye and look at your retina and your rods and cones and see how healthy your eye is. Okay, so a dilation is either an enlargement. Okay, and that happens when your pupils get larger to let in more light, right, in the dark. If you walk into a dark room, your pupils have to open up as much as they can to let in as much light as possible so you can see, because without light you can't see. Not only is it an enlargement, it's also a reduction. So when you go to the optometrist and your eyes are dilated, yes, your pupils are enlarged so that you can see. But when you walk outside from a dark room into the bright sunshine, right, what do you have to do? You usually close your eyes a little bit to let in less light while your pupils dilate, aka reduce in size, so that you can see properly. So this happens to your body all the time so that you can see. Okay, we have dilations. A dilation creates similar figures from a central point. Right, so this is getting larger or getting smaller based upon what's called your scale factor. Scale factor. And they are giving the variable k to be your scale factor. On your project, that's what SF stands for. Scale factor. Okay, is how much larger the figure is enlarged or reduced. Okay. If your k is less than 1, it's a reduction. You're getting smaller. If k is greater than 1, it is enlargement. Your thing is getting larger. The notation is k times x and k times y. Okay, so kx and ky is our notation. You are multiplying each point by your scale factor. So here we have a scale factor of 3. Okay, so your notation is going to be 3 x's and 3 times y. So here we have point A. Point A is at 2, 1. If you multiply all the points by 3, that means we're now at 6, 3. Here is your A prime. Okay, point B is at -1, 0. Multiply each point by 3 and we get -3, 0. So B prime is right there. My students just told me that I did something bad. So I'll fix it. A is not at 2, 1. It's because the height is squished. My eyeballs didn't see it. I apologize. 2, 2 says my studious students. So 6, 6. Here is the point of A prime. That looks like 6, 6. Is B correct though? B's right? -1s? Okay, good. Now we have the point C at -3, -2, right? That's point C. Positive 3, positivo 3. So C prime is going to be at 9, -6. We are multiplying each of your coordinates by the scale factor. Okay, multiplying each of your coordinates by the scale factor. Okay, so this triangle, the side lengths are 3 times as large as they used to be. Okay, each of your coordinates is 3 times as far away from the origin as they used to be. Okay, so this is how we do a dilation. You multiply each of the coordinates of your points by the scale factor, and you plot it and you shade it. So we're going to do that here. Now we have a scale factor of 1/2. So now all of our points are going to be half as far, twice as close, whatever, is going to be closer to your origin than they used to be. Okay? So let's see what happens there. So there we go. Now, I know it's not very important, but if you draw a line from your origin through your vertices, right, through your original and then through your dilated, you will see that they should line up exactly on the same line. Okay, kind of like you're doing an art project with 1 point perspective. Okay, they all go back to that same point of the origin. If you're into art, that's kind of fun to do. Okay? So now let's do some, there's another example, 3/2. Okay, let's do 3/2, but it's done the same, so let's not do it. Just kidding. Dilations with the center not at the origin. So once again, we're going to count. This is going to be a counting thing. So -4, 6 is your center of dilation. -4, 6 is right here. This is where we're going to count from. We want to do it with a scale factor of 2. So each of your points is going to be twice as far away from your scale, right, this point, your center of dilation. And we're going to do this by counting since it's on a grid. How far is point A away? That is 1, 2, 3, 4, 5 right and 2 down, right? So 5 right and 2 down. So I'm going to multiply those distances by 2 and get 10 and 4. So there's 10 right, and here's 1, 2, 3, 4 down. So here's our new A prime. Right, we're counting our horizontal and your vertical distances traveled from your center of dilation. So point B is 1, 2, 3, 4 down and 2 right. So we're going to go 8 down and 4 right. We are multiplying our distances traveled in every case. Then C is 1, 2, 3, 4, 5, 6 right. 1, 2, 3, 4, 5, 6, 7 down. So that's going to be 12 right and 14 down. 8, 9, 10, 6, 7, 8, 9, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6. C prime. Okay, so we are counting how far horizontally and how far vertically is our original point away from your center of dilation. Okay, because you still should be able to draw a straight line from your dilation point through your C point and then your C prime. So let's see if we can do that. Let's see. So here is your line from origin to B. Does that line up with B prime? Looks like it. Here's your line from A to A prime, right? That looks like a straight line. And then you have from C to C prime. Yeah, looks like it's pretty good. Okay, so there's some dilations with a center not at the origin. Okay, that is all. 25 minutes is pretty good. Okay, bye.